And now we have research paper from Clemson University, Georgia Institute of Technology, and BMW Research Center, viability of Azure IoT Hub for processing high-velocity, large-scale IoT data. So you could pick up it from here.
Thank you, Alex. So I'm Daniel Smith, and joined by Wajdi Halabi and a few of the other folks that worked on this paper. Wajdi is going to share the slides, and then we'll get started.
Can I see this?
Okay, it's loaded now. All right, so good to see everyone today. Today we're going to talk about our paper on the viability of Azure IoT Hub for high velocity, large scale IoT data. And on the next slide, just a brief overview of the contents. We'll talk about the motivation for our paper. We'll give you a background on Azure IoT Hub, and we'll go over the software and architecture of a client data generator that we produce to mimic a manufacturing plant sending a large workload to the cloud. And then we'll discuss our experiments and the results that we got in those experiments, and briefly end with a conclusion and some time for questions at the end. So if we move on to the next slide. The primary motivation for our paper was the concept of the digital plant and the rising trend of Industry 4.0. Manufacturing plants are starting to connect thousands of sensors to the cloud so that they can send data for analysis use cases such as predictive maintenance or status dashboards. And the goal of our paper wasn't to do that analysis, but to analyze, or rather to examine Azure IoT Hub, determine its viability for handling such large workloads from manufacturing plants. So we worked closely with our BMW partners to assess what the needs would be in a manufacturing plant in these use cases. And then we used the Clemson Palmetto supercomputer in order to generate a large workload that would resemble thousands of sensors sending data to the cloud from a manufacturing plant. So if we move on, next slide. Now I'm going to talk and give a little bit of background about Microsoft's Azure IoT Hub solution. IoT Hub is a managed service, and one IoT Hub can have multiple deployed instances called units. These units, basically, they allow you to scale up your throttling limits if you need more throttling limits in the cloud. So if you had 3 units of IoT Hub, you'd have 3 times higher throttling limits. And next slide. Then I also want to talk about sensors. Sensors are the ones that are sending data to IoT Hub. And in Azure IoT Hub, they have a unique device ID. They also have each sensor has its own secure access token so that they can communicate with IoT Hub securely. And the preferred protocol for communicating with IoT Hub is MQTT, although HTTPS and AMQP are options. And one thing to note is that sensors, they link up to one IoT Hub, not the units, but the IoT Hub. Next slide. And now pricing. If you're considering IoT Hub, pricing is relatively simple. IoT Hub pricing is not based on consumption, but rather it's a flat monthly rate. IoT Hub comes in 2 tiers, basic and standard. And the only difference between these tiers is feature set. For example, standard allows IoT edge deployments and some cloud to device messaging. But each of these tiers offer identical additions. There's additions 1, 2, and 3. And the difference between the additions is their throttling limits. So if you were to choose IoT Hub as a cloud solution, the flat monthly rate would be based on the tier of IoT Hub, the addition that you choose, the region that you deploy IoT Hub into, the number of units of IoT Hub you have, and of course, the number of days that you keep IoT Hub provisioned. So next slide. Just a quick note about the throttling limits. As I said, they're determined by the edition that you choose. And so for example, say you had an edition 3 IoT Hub, whether it be basic or standard tier. As an example, that would give you 6,000 send operations per second per unit. And that would also give you 300 million messages per day per unit. Next slide. And lastly, a big part of IoT Hub's design is their partitions. Partitions are the event logs that receive data from sensors that read the data. IoT Hub can have anywhere from 4 to 32 partitions if you create it through the online portal. Although do note that you can actually provision up to 128 partitions if you use the command line interface. And one thing that's great is that partition count does not change the price of your IoT Hub. Although, once you've deployed your IoT Hub, the partition count is fixed. You can't change it. If you want to change it, you need to deploy a new IoT Hub. And then an important note that will come up later when we talk about our experiments, each sensor in IoT Hub is hashed to a specific partition. So a sensor that sends data to IoT Hub, all that data will go to one partition. And like I said, more on this later. So next slide. Moving on, I'm going to talk about the software and architecture of a client data generator that we made to send a large workload to IoT Hub. Firstly, a note about Clemson's Palmetto supercomputer. It's a multi-node, high-performance computing cluster. We leveraged it so that we could emulate thousands of sensors using up to 10 nodes. And we wanted to test the network. So we sent pings from the Palmetto supercomputer to an Azure VM in the ECUS2 region, which is also where we had all of our IoT hubs in our experiments. And we found that it had a consistent average latency of 20 milliseconds. Next slide. Now, the actual client data generator itself. We made the data generator to represent a single physical sensor, which means if you have thousands of instances of this generator, they simulate thousands of sensors in a manufacturing plant. For that reason, we wrote the generator in C++ to keep a low memory footprint and also take advantage of multi-threading. And we made this generator to accommodate a variety of parameters that would mimic real sensor behavior. And again, we'll cover those in our experiment section. Next slide. And lastly, for me, we wanted to validate our generator. So our client data generator, it gives inner message gap times that follow a statistical distribution. It can be either a constant distribution or a Pareto distribution. And you specify the distribution you want in the parameters. So we use TCP dump to verify this by measuring packet send times. And sure enough, once we gathered those packet send times and we modeled them, we confirmed that the distributions of the generated inner message gap times were the same as those distributions that we specified in the parameters. Next slide. And so now I'll hand it over to Wajdi to talk about our experiments.
Thanks, Daniel. So every one of our sensors will be going through this experiment loop you see here. So our sensor will generate and send a JSON string to IoT Hub, and then we log that send time down to the millisecond. And then behind the scenes, the Azure IoT Hub SDK creates a asynchronous thread that's listening for a response from IoT Hub. That response will either say the message was processed and everything's good, or that the message was not processed and destroyed. So that will happen if we exceeded our throttling limits or if Azure rejected our message for any other reason. So we log that status as well as the time we received that callback. And the difference between our receive time and our send time is our IoT Hub round trip latency, which we use as our indicator for how well IoT Hub is performing. Meanwhile, during that, the main thread is just sending a message, sleeping for X milliseconds, sometimes it's 10, other times it's 1,000, depending on the experiment, and then sending the next message. And it will continue doing that until an elapsed time has passed, usually 3 to 5 minutes. We want to measure round trip latency when steady state has achieved. And the first few messages have much higher latency than the rest of the experiment would. So we dropped the first 5% of messages since they are not indicative of what a real world performance will look like. All right. So here we test what happens when we vary the message size. So we have a 512 byte, 2048 byte, 8192 byte, and 32,668 byte message sizes. And we test them against basic edition 1, basic edition 2, and basic edition 3. And remember what Daniel said, that these editions only differ in terms of throttling limit. Their feature set is the same. We keep all of our experiments use 10 sensors. We're sending at an inter-message time, or IMT time, of 200 milliseconds, and we run it for 120 seconds. So we noticed that B1, B2, B3, if you keep them below the throttling limits, all follow similar patterns, which is this previous table show you see here, where 95% of messages have a latency less than 60 milliseconds, regardless of message size. So the next factor that we test on is varying the intermessage gap time, or varying the frequency that we send these messages at. So we chose a high frequency with an intermessage time of 10 milliseconds, a moderate one of 100 milliseconds, and then a slow frequency of 1,000 millisecond gaps. We keep the message size constant at 2048. We use the highest throttling capacity, so B3, and we run these experiments for 300 seconds. What we noticed was that in our 100 millisecond interval and 1,000 millisecond interval runs, we had very few spikes. You see here on the graph, these are our blue and purple lines. While the 10 millisecond IMT runs had frequent periodic spikes. We reached out to Microsoft about this, and what they came back to us was that the way partitions work is that a device is hashed to a certain partition, which means when that happens, all the messages from that single device will go to this one partition. So at very high frequencies, we can fill up that partition and the messages need to be flushed. So that's that periodic, the latency climbs and then suddenly drops again, spikes you're seeing in orange. Which leads us to our next point. What happens when we vary the partition count? So here we focus on the high frequencies, since you can really see the results at low frequencies. We have an intermessage time of 10 milliseconds and 333 milliseconds. And we tested against IoT hubs with partition counts of either 4, 8, 16, or 32. Message size is constant. We're using B3 again, and our runtime is about 300 seconds. So it's important to remember that there is no load balancing between the partitions. In the worst case scenario, all the messages might go to one partition if all the sensors were hashed at one partition, which leads us to our group A experiment. In group A, latency, mean of 10 sensors. So we have 10 sensors with a constant IMT of 10 milliseconds. So we're sending about 100 messages a second a sensor, or IoT hub is receiving 1,000 messages per second overall. Our IoT hub with 32 partitions managed to handle the load well, that blue line on the bottom. However, our IoT hubs with 4, 8, and 16 partitions do not. With the 4 and 8 partition ones having latency climb as high as 30 seconds before suddenly dropping, but still only going to an average latency of 10 seconds and then starting to climb again, which could threaten any kind of soft real-time deadline you have in place for your IoT messages. On the other hand, group B over here has a latency we tested 1,000 sensors and at a constant IMT of 333 milliseconds. So each sensor is sending about 3 messages a second, but since there's 1,000 of them, IoT Hub is receiving 3,000 messages per second, which is triple than the total amount received by Group A. And even with that, you notice that the average latency rarely rises above 60 milliseconds across all of our IoT hubs, which further shows the point that IoT Hub is best equipped to handle a large number of sensors sending at a moderate rate. It's best equipped to scale horizontally as opposed to scaling vertically, where we have a small number of sensors sending at high frequency. And the principal motivator behind all this was, what if a manufacturing plant were to deploy thousands of IoT sensors in their assembly line? So here we focused on scale. So we have experiments with 2,000 or 4,000 sensors sending to IoT hubs with multiple units. Up until now, we've only used one unit or one instance of IoT Hub. Here we're going to use multiple ones simultaneously. So like Daniel said, an IoT Hub unit just scales linearly with your throttling capacity and your price. So 2 IoT Hub units would be double everything, more or less. And also on the client side, to run this many devices, to have the memory capacity, as well as to make sure that we don't have any bottlenecks on the network side, we're using multiple nodes simultaneously. So each node on Palmetto has its own RAM as well as its own network card to prevent any bottlenecks on the client side. We kept the IMT constant 200 milliseconds, so relatively moderate frequency, and message size is constant. We're using a 4-partition B3 IoT Hub. So overall, we're sending 10,000 and 20,000 messages per second, respectively. So that keeps it at about 80% of a B3 throttling capacity. And yet IoT Hub behaved stably, with 85% of messages having a latency of 100 milliseconds. And you can see, even once we split those 2,000 sensors across 1 node, 2 nodes, or even 4 nodes, that the results do not really change. So no matter, IoT Hub is able to process it all. And with that, I hand it back to Daniel.
Thanks, Wajdi. So in conclusion, we find that IoT Hub, like Wajdi said, is designed to scale horizontally. And this is a big benefit to manufacturing plants, as they not only have a large number of sensors, but they will probably add hundreds, thousands of more sensors over time. And we would recommend from our experiments, our findings, that individual sensors, when they're sending to IoT Hub, should avoid sending at a high frequency. Now, if you were to provision your IoT Hub with an appropriate partition count, say 32 partitions, then your IoT Hub may be able to handle high frequencies. But if you do not take that into consideration, then IoT Hub will be overwhelmed by the amount of data coming in per second, which will cause processing delays, and you might miss some soft real-time deadlines. Also, we want to note about IoT Hub. It's relatively simple to determine what configuration you need for an IoT Hub deployment, and also what the flat rate cost will be. Last thing we want to mention here is that our client data generators, source code, scripts, and data are all public and available at the following GitHub link. So last slide. I want to say thank you for listening to our talk today, and we're going to open it up for questions.
Thank you. So any questions?
So I could see this with a question. Can you guys tell us a little bit more about the client generator and how you were able to pack generator instances into individual compute nodes? What were the constraints? What were the limiting factors on that?
Much do you want this or me?
I'll take it, sure.
Okay.
So one of the biggest limiting factors was just the memory. Even though we wrote it in C++ to have a small memory footprint as we can, every time we sent a message, we had to add another space onto the stack so we can listen in for that callback. So at sitting at high frequency, we just actually ran out of RAM once we started working with hundreds of sensors. So it's just being able to fit all that onto one node was most of the challenging part. And actually, we didn't want to risk bottlenecking the network card. So that's why we use multiple nodes, especially in the scaling experiments. I think we could run about 1,000 sensors on a single node.
Yeah, it was about 1,000 was what we found to be a good number, and we would run these. We would run instances of the client generator by just running through bash each instance as a background process on the node. Thank you for your question.
Any more questions?
If I followed the reason for the spikes correctly, the spikes in response time were due to some flushing that was occurring. If you had modified the message size at that point from 2048, would you have seen a change in the frequency for the flushes?
That's a good question.
Yeah.
It's hard to say if the partitions. I'm not sure if it's determined by the count of messages that come in or by the amount of data. Although, Wajdi, help me think here.
I think it's the count.
Actually, doesn't IoT Hub, they number messages, I think, as you increase in size, I believe there's for IoT Hub, it's about 4 kilobytes. And once you hit that limit, messages are fixed at a certain size. So like if you have more, if you send one message that's greater than 4 kilobytes, it'll count. Like if you send a 5 kilobyte message, it'll technically count as 2 messages. So if you increase the size of the message that you send, I think it would be very possible that the partition, like those spikes, would become more frequent.
Yeah, I would agree with that.
Thank you.
Thank you for your question.
Thanks.
Okay, thank you very much. So I think it is time for next session.
All
right. Thank you so much.
Thank you.
Hamza, will you take from here?